our head of PR, Inge, asked me to supply an abstract, and I did so, and my PhD student, Norrie Rothbart, read that slightly later and came to my office and asked whether I was drunk when I wrote it. So, as a common theme in this talk, we will go through various parts of this little abstract. So let me just read it aloud to you so you remember it. So, theory of computation concerns the mathematics governing computing in this universe and in other universes you may dream of. The lecture will cover why this is sometimes relevant to the audience, that's you, why it is often irrelevant, and why the latter, it being irrelevant, is sometimes a good thing. And the final part of the lecture will concern the particular professorship, the job, inaugurated with this talk, and how I intend to use it for the greater good. So let's talk about the theory of computation. So in the abstract, I told you that theory of computation governs or concerns the mathematics governing computing in this universe. So there are multiple facets of this, and what I am going to talk about is one small fragment of it, the fragment that we are mostly interested in my group. However, there are other parts of the theory of computation involving other sciences, physics, applied mathematics on hardware, numerical analysis, and many more. In the field of computer science, theory of computation usually refers to one specific facet, the study of what computers can do, what they can compute, and how efficiently they can compute it. The converse of this is that theory of computation also concerns what computers cannot compute, and how inefficient they are sometimes forced to be. Again, there are other people, even at our own department, who do similar things, just different facets of the theory of computation. We have a great algorithms group, we have a great programming language group, all of whom use slightly different aspects than what I'm going to talk about today. Now, most of you already carry a computer, right? You carry a specific device, this is a smartphone, which is a computer more powerful than even the fastest supercomputer of 25 years ago. Most of you have laptops, most of you have, well, some of you have watches that may also contain extremely powerful computational devices. So most of you probably know or think you know what a computer is, right? Only a few should be surprised that I mentioned that your smartphone is a computer. However, a computer is not merely what you think. To your right, you have several kinds of so-called logic gates, right? So the computers you have are roughly made of large numbers of logic gates. Each logic gate, if you have a look, comprises, well, there's a symbol and a name, and then there's a small table. The table is the input-output function. It says that if the gate, so the mathematical entity, a gate, gets certain input, then it should output something specific. And different gates are characterized solely by the action of their input and output function. It doesn't matter how they are actually implemented. So the logic gates are only defined by the input-output functions, the small tables, not the substrate they are made from. So when you think of your computers, you probably think of the concrete physical devices and the electronic circuits and electronic gates that they're made of. But overlaid on that is a sort of purely mathematical description of the logic gates that enable computation. Now, the property that the gates are only distinguished by their input-output function is a phenomenon called extensionality. And if you only remember one word from this lecture, please let it be extensionality. I will talk a lot about this. However, as soon as you understand what a logic gate is and how it works, you tend to see them everywhere. And at least if you're a computer scientist, you tend to try to cast every process you see as something that can do computation, for instance, a logic gate. So this means that if we see a phenomenon that we can use in the physical world to model a logic gate, and we can do it in such a way that we can compose them together, we can in principle build computers from completely different things than what you're used to. One example is the picture on your top right. That's a billiard table. Now, some years ago, some computer scientists found that you could actually encode arbitrary size logic circuits made of logic gates using sufficiently many billiard balls on sufficiently large billiard tables. Now, what is input and output? Obviously, this has to be encoded in the angles and speeds and so on that you send the billiard balls out with. And the actual computation then happens when billiard balls collide. And since kinetic energy is more or less conserved, it's a good approximation, these billiard balls collide, and the angles and speeds with which they then propagate throughout the billiard table is completely deterministic and well understood, so that after a certain time you can basically read off the billiard table and the moving balls what the output is. So we can build basically any app on your smartphone using a billiard table. Now, this of course can be taken further. There are certain kinds of crustaceans that move in a very deterministic manner. So I can take a bunch of crabs, and provided that they have enough energy and that I enclose them in a certain space and that I initially propel the crabs forward with my hand or a little cannon, a little crab cannon, in a certain direction, then when crabs collide, they recognize that they see another crab and they basically just go out like billiard balls. And this sounds like complete madness, of course, but you can actually build a computer from crabs. And people did that in the real world. So the concrete paper here is Robust Soldier Crab Ball Gate. This is an actual scientific paper. If any of you know the Ig Nobel Prize, this would have been a candidate or should have been a candidate. But they actually took the crabs and built computers from them. Now, unfortunately, crab computers don't scale very well. They're slow, and hence if you try to perform a really tough computation like implement, say, Flappy Bird on crabs, crabs tend to sort of die or lose interest in moving before you actually can play the game. However, in principle, given sufficiently efficient crabs, this can be done. A variation on this is not using sort of the kinetic energy preserving collisions of billiard balls, but interactions of particles that that repel or attract each other. So you might imagine two particles whose attraction is governed by the usual inverse square law that we have in physics. Inverse square law as in, for instance, gravitation. And if you send these towards each other in a predictable trajectory in such a way that they don't collide, you can actually completely deterministically compute how they sort of slingshot off each other, right? So those of you interested in astroscience might know the sort of gravitational slingshot effect that's sometimes used to propel spacecraft. You can do the same with basically any object, and as long as they don't collide, because that would be silly, you can actually also build computers from logic gates made from these things. So if we dream big, you can make a computer out of these. One of the unfortunate problems with the cutbacks in research funding is that there are no papers that actually did this for real, because we couldn't get funding for the required number of planets. Also, it has the problem that you sort of destroy the computer after running it once. But in principle, it can be done. So, on a less expensive note, there are many kinds of computers, all of which can, in general, compute things in physically very disparate ways. But there's an underlying mathematical theory about how these things work that we can use to sort of say what kind of computers can compute the same things as others. Some less exotic examples you might have heard of are biological computers, quantum computers, and so on. And these are just other examples in case you don't want to build a computer out of planets. All of these systems are subject to the same theoretical limits to what they can actually compute. And all of them have a notion of program. Now, I told you to remember a specific word a few minutes ago. Does anyone remember what that word was?
Extensionality.
There's a finger. Extensionality, thank you. Now, I also would like you to remember the word program. That might be slightly easier. Okay? So, the idea, the seed idea I hopefully have planted in your brain right now is that a computer is not necessarily what you think, and a program on an exotic computer might be something completely different in nature to what you're used to. However, the kind of mathematical laws that govern these are the same regardless of the actual computer. Okay, so this talk is about computers and programs in the most generally thinkable way possible. And with that, we come to part 2, the path of now and forever. So, this is a talk that should be accessible to laypersons. But even a layperson who's averse to technical or mathematical material would do well to ask, that's fine, computers can be many different things. But what do you actually do in the theory of computation? Well, in general, we seek to prove mathematical statements called theorems that ideally concern all the various notions of computation that we can think of, at least the ones that are realizable in the physical world. And the validity of such theorems is eternal. So the scope of such research is not the current technology or next year. It is doing something that in principle holds forever, though sometimes we must go after smaller targets. We cannot always do it for all notions of computation. And even if we prove something that in principle is true forever, someone else might generalize our results and we will sort of be forgotten. But that's fine because we'll be dead by then. Now this goal of proving things that in principle are valid forever is similar across all the branches of theory of computation. So algorithmicists do the same thing, computability theorists do the same thing, etc. But they're interested in various facets and use different techniques. This also goes at our local department. So you might look at people who don't say they are using theory of computation, but in reality they are. They just have different focuses. So we have in computer science, as we say in Danish, sejret os selv til døde. So computer science as a science has been subjected to an explosion in interest from the public for what we do and the actual physical artifacts that we're interested in. And this means, especially in the public eye, that computer science as a science is sometimes seen as a very, very modern thing, always at the cusp of the wave of technology. However, computer science and theory of computation itself is a venerable pursuit. It is old. To your right is the one paper that is generally regarded as the start or the seed of the science of computer science. This is Alan Turing's on computable numbers with an application to the Entscheidungsproblem from 1936, prior to any actual, physical electronic computing machines had ever been built. Alan Turing's work was part of a 20th century program, a research program among mathematicians who wanted to do so-called meta-mathematics, using mathematics to reason about mathematics itself. Alan Turing himself was a mathematician originally. He was also a world-class long-distance runner, by the way. In his time, the word computer was usually only used for a human specialist, typically sitting in a back office with what we today would call an algorithm, and they would do what we today would sort of call run by hand, håndkøre, this algorithm in order to do computations that were of relevance to whoever wanted them. It was typically a woman. So the modern device that we call a computer was, for most of Turing's life, he called it an electronic computing machine. to distinguish it from the word computer that was actually used for humans. The paper, apart from being brilliant in all sorts of ways, also started a time-honored tradition of looking at programs as data. So a program, whatever that may be, on whatever notion of computation we have, is something that we can represent as a piece of data we can feed to other programs, or even feed to the program itself. And the Turing's 1936 paper, I think, so it was heavily inspired by work of Kurt Gödel about 5 years earlier, which is even cited on the first page, right? Über formal unentscheidbare Sätze der Principia Mathematica und verwandter Systeme 1, where similar techniques of self-application was used in a totally different context in mathematical logic, also in the area of meta-mathematics. Now, the idea of self-application, having a program applied to itself or to its own code, it's one of the best ideas ever, right? So we might imagine if Turing wrote this down and walked into the back office and gave whatever computer, whatever woman they had sort of put to do this, and in the instructions it said, now take this piece of paper and use it as input to itself. And I guess that she would think that someone had played a prank on her. This simple fact of self-application and the use of programs as data is one of the great ideas of 20th century mathematics and engineering. Now, these breakthroughs, Alan Turing's was not the only one, right? We also mentioned Kurt Gödel's, and there were several other breakthroughs around 1936, 1937 from American universities on other notions of computation, called recursive function theory, lambda calculus, and so on, that were only later, well, actually later, in 1937, 1938, shown to be equivalent to the notion of computation that Turing introduced. But they built on a long tradition, not just in mathematics, but also in philosophy. So meta-mathematicians were active even earlier. Well, they didn't call themselves meta-mathematicians in the late 19th century, but the logicians working on formal systems were actively creating notions of algebra and logic that could very easily be turned into what we today would call a programming language. One of the foremost of these was Gottlob Frege, who, when you look at some of his material, for instance, so I've mentioned the Begriffsschrift up here, this is just one example, contains material that, if you're a student here, would be very easy to turn into a purely functional programming language, for instance. And if you squint at it the right way, and if you are a bit generous, you can find vaguer notions of having systems of thought applied to other systems of thought, as far back as the scholastics in the medieval times. So I mentioned Thomas Aquinas here, but he's only one example. So computer science and theory of computation itself is a science with a history spanning 80 years from Turing and historic rules spanning centuries. So the fact that you and everyone else in the Western world, at least, carry an advanced laboratory with which to perform such science does not make computer science subservient to your pleasure or the pleasure of other sciences using computers. We will help you, just don't be arrogant about it. Computer science is a venerable science with a life and justification of its own. Now, what do we actually do? The poster child for an quote-unquote interesting theorem in the theory of computation is Rice's theorem. So note that we've now moved from 1936 to 1953. A great leap in time, and buckle up, guys, right? We need to cover 63 more years in this talk. Now, Rice's theorem, incidentally, they published papers with exquisitely boring titles back then, right? Classes of recursively enumerable sets and their decision problems. It is very to the point, right? What is Rice's theorem? I'm going to state a version of the theorem that is understandable in a moment, but we need to have a little run-up to it. Do you remember the circuits on the right? It's just 5 minutes ago you saw them, right? So you should remember them. Do you remember the word extensional? And you roughly remember what the word extensional means. So extensional is something that only has to do with the input and output function of the program. So circuits are extensional, right? The little tables on the right of each circuit is the only thing that's defining the circuit. The actual implementation of the circuit is something else. That's what we call a program. There are many different ways of building the same circuit. Your way may be different from mine, but they all share the same input-output function if we're implementing the same circuit. Now, not all programs are circuits, though all physical computers we know of are made from these, right? Programs could be texts that we know how to execute in certain ways. Programs in general on your computer will have infinitely many possible inputs. For instance, positive integers, 1, 2, 3, 4, 5, and there's a priori no limit on the number of inputs you can feed it. There will, in practice, of course, be a limit because your computer has finite memory, but for theoretical purposes and also for programming, if you've ever written a program, it's sometimes just easier assuming that a program can have infinitely many inputs. So, this means that programs in general, if we had to write up the little tables up there that specified the input-output functions, would have infinitely large tables. This is not exotic. This is just how it is on almost all programs that you have running on your machines. Now, what do we want? I talked about self-application before and generally using programs as data. What we want is to have programs decide properties of other programs. So I will be slightly vague about the word property. I hope that you will at least have some understanding of what I mean. A property could be that a program is 10 characters long, or that it computes the identity function. Okay? So a property of programs is decidable if there exists some program P that, when given any other program, says yes if the input program has the property you're interested in, and says no otherwise. So it gets the program as input, it then computes for a while, but only a finite amount of time, and then it says either yes or no. And this, of course, can be done for many other things or objects than just programs. We can do it for lots of different sets and so on, but let's just stay with programs for a while. Now, extensionality. Everyone remembers it. So, to be a bit more specific, a property R of programs is extensional if for all programs P and Q, if P has property R and Q has the same input-output function as P, then Q also has property R. So the property is only about the input-output functions, nothing else. So a bit more intuitively, a property R is extensional if we cannot use the property to distinguish behavior between programs that have the same input-output function. So for instance, the following properties are extensional. P outputs the word shibboleth on all inputs. Right? This is only about the input-output function, no matter how we actually implement it. Another property that's extensional is on input x, P output x. So P is the identity function. P loops infinitely on input 2, extensional. P outputs 3 when given 1 as input, also extensional. Okay? Because these properties only concern the input-output function. Certain properties are not extensional. For instance, whether P runs for a specified amount of time, or whether P contains a certain number of instructions. These are not extensional. These are what is called intentional properties. Rice's theorem, and incidentally, if I'm boring you, a fun exercise is to go on Wikipedia, which supposedly is an okay online resource, and try to understand what it says about Rice's theorem. Actually, this means that maybe someone working in actual theory of computation should edit Wikipedia from time to time. But this is the best I could do for a general audience. Okay? So Rice's theorem says that if an extensional property of programs is decidable, then either all programs have this property or no program has this property. Okay? Decidable, right? A decidable property meant that it was a program that said yes or no on the input, depending on whether the input had this property or not. right? So decidable properties are essentially those that programs can, well, decide without human aid in finite time. And this theorem says that, well, if you have extensional properties that are decidable, then they're uninteresting. The only such properties are those that either all programs have or no programs have. So this is an earth-shattering theorem the first time you see it, because usually when you start coding stuff, programming when you're young, what you think is, oh, if I'm just clever enough, or if I just use this hack, I can create a program that can really do some fun things, and then you find out that this theorem can actually be used to thwart most of these things. It's impossible. So the above Rice's theorem will hold for what you already think is a program or app on your phone using your favorite programming language on your favorite computer. It will also hold for all the other things we can regard as general purpose computers and regard as programs. And it will also hold for the woman sitting in the back office running algorithms by hand back in 1936. So even she can't do it. Even she can't decide any interesting extensional properties. And there are many more theorems like Rice's, right? This is one of the earliest general theorems that shows that certain things are really, truly impossible on computers. So that was 1953. What do we actually really do here at DICO? Well, Rice's theorem was about extensional properties. Okay? So they concern what is computed, the input-output functions. This has been studied for more than 60 years. So what we do currently is mainly trying to crack a harder nut. We want to prove theorems about intentional properties, how things are computed, how efficiently they can be computed, what programs actually do when they compute. So one specific example of intentional properties is computational complexity. The study, roughly, of classes of problems that programs can decide on computers using limited resources, right? So Rice's theorem just said any program deciding things, running as long as you want, can or cannot do something. But in computational complexity, we're usually interested in having very specific upper or lower limits on the amount of resources programs can use, time or space. So if you recall the path of now and forever, we want results that hold for as many different kinds of computers and programs as possible. The trouble with intentional properties is that these tend to be slightly different on different computers. So these tend to be very sensitive to the kind of implementation you can do on different machinery, whether you do things on crabs or planets or in C++ versus Java or whatever you like. So for this reason, when we talk about limited resources, we usually need to give them a little leeway when we talk about resources. For instance, some of you might say, but couldn't we, with great success, look at, say, the set of programs that ran in linear time, or quadratic time, or cubic time, or exponential time, or any specific function that you might care to mention? And of course, yes, we could. But the problem is that these bounds are very sensitive to the actual kind of computer that you use, even with real-world computers and real-world programming languages that we have on our current computers today. So the way out of this is to give a little leeway and allow our notion of limited resource to have so-called closure properties. Basically, a closure property means that you can perform some limited transformation on the resource you're looking at, say linear time or quadratic space, and the resource bound should still result in, or should still be in the class you're considering. So for instance, the most famous example of this is the set of polynomial time decidable sets. So P, as it's called, is the set of finite bit sequences decidable by a program that runs in time bounded by a polynomial in the size of the input. For those of you who don't remember what a polynomial is, remember high school, right? Or even earlier, ax squared plus bx plus c, that's a polynomial. So it's 5x plus 2. and so is 10x to the 1,000. So the class of mathematical functions that are called polynomials are usually necessary. It's usually necessary to consider such a large class of possible resource bound in order for the class of sets or problems that you're looking at to be invariant across the different notions of computers you look at. One very early example of why this is true is actually back from, it was proven much later, but they already knew it back in the 40s, which is that if you take one of the computers that Turing defined, so-called Turing machines, that basically have the same power as modern computers, and you roughly look at such machines having one hard disk, or one tape, if you will, and another variant having two hard disks. There are problems that the one with two hard disks can solve in using fairly efficient resources, namely linear time, that the one with one hard disk cannot, where it has to use quadratic time. For instance, recognizing whether a string is a polynomial. So again, this is quite old. Now, the class P of problems is just one example of the kind of stratification that we as computer scientists use in order to distinguish the hardness or difficulty of solving different problems. Now, of course, there are quite a few of these. On your right is a small selection of such classes. So the black ones denotes the class of problems. So P, NC, AC1, NL, L, X time, and so on. And the blue, red, and I don't know if that color is actually pink. Is that color pink? Not really. What would you call that color? In the very top, near the words arithmetic hierarchy, you will see FO of n for first order logic. What is the color? Purple? Yeah, never put a colorblind man in this situation. So the black letters denote various classes of problems that we as computer scientists have identified throughout the years. Some of these, well, we actually don't know whether they are the same class or not. And some of these are quite famous as well. The famous P versus NP problem concerns, well, the class P that we just mentioned, which is on your right. Up here, there's a P. And if you just sort of go diagonally up left, you will see something called NP. It is above P in this little picture, because it is at least as large as P. It contains P as a subset. We actually don't know whether they're equal. This is the most famous sort of unsolved problem in this area, and also one of the most famous unsolved problems in computer science. Now, have a look at the other colors. The other colors denote so-called logical characterizations of these classes. So mathematicians and some computer scientists have looked at whether one could define these classes in ways that did not specifically refer to the kind of machinery used to compute them. So originally, these classes were defined in terms of specific constraints on the resources you could use, right? Like quadratic time or polynomial time. But maybe if other characterizations were found, it would be possible to use the full power of mathematics, the fully armed and operational power of the battle station of mathematics, to try to attack some of the open problems in this area. So far, we've been fairly unsuccessful. But the point of this is that what we do here is essentially variations of the colors up there that are not black. We try to find characterizations of problems in computer science, or classes of problems in computer science, without having specific attention to the kind of machinery used to compute them. So this is what we actually really do here. We prove new theorems on intentional properties for programs. I'll give you an example in a moment. And we devise new ways of characterizing classes of problems that can be solved with limited resources. So what's a characterization? I'm going to be deliberately vague about this because we don't have all the time in the world. It is typically a logic whose sets of models, if you know what that means, of true sentences corresponds in some way to the class of problems. Or it could be a new programming language that allowed, where the allowed programs you can write in the programming language can compute exactly the programs or decide exactly the programs in the class. Or it could be some set of pre-existing algebraic constructs from mathematics. It could be many things. So I promised you an example. You're going to get one here and one in a moment in the next part of the talk. So we talked about Rice's theorem before. And what we want is, well, intentional versions of it. Basically, a theorem that says that certain problems can never be solved on any reasonable kind of computer, but these problems, well, has to concern properties that are not necessarily extensional, but intentional, right? That they concern how things are computed rather than what is computed. So, for instance, you could look at the set of programs running in polynomial time. So programs that when you run them and they compute for an amount of time which grows as at most a polynomial in the size of the input. It's very well known that the set of programs on any programming language you might think of or could devise right here. I'm willing to prove anything about any programming language you might devise. That the set of programs running in polynomial time is undecidable. It's not hard to prove. However, there's kind of a pipe dream. And there are many researchers who are engaged in doing approximations of this set. So under or over approximations. An under approximation of the set of polynomial time computable programs is a set of programs that can compute, well, maybe even all of the polynomial time computable input-output functions, but maybe doesn't have all the programs in there. And that's kind of nasty, because, for instance, you might have your favorite sorting function. And, I don't know, your favorite sorting function is probably quicksort, or something like it. Bucket sort, anyone? Or other variants. And usually what happens with these under approximations is that some of these programs are not in the under approximation, quicksort being the perennial example. So your favorite program might not be in there, even though there will be a sorting function which might be efficient inside the under approximation. Another thing is over approximation. So the pipe dream is that we could somehow have a decidable set of programs that strictly contained the set of polynomial time computable programs. Polynomial time programs. Right? So what would that be, the over approximation? It would be a property that basically said for each program, this program either runs in polynomial time, so fast, or it might use more time, right? Run slightly more slowly, but has some other decidable property. So we would get all the polynomial time programs plus maybe a few junk programs that wouldn't really matter. Now, let me just give you an example of a very recent intentional theorem. I'm not going to explain the technicalities, I'm just going to talk about the consequences. So with Jean-Yves Moyat, who's in the audience, Jean-Yves and I recently proved a result stating that any non-empty partially extensional decidable set is extensionally complete. Now the word extensional is in there a lot. So of course, what has this to do with intentionality? Well, the funny thing is that even though the word extensionality is in there a lot, it is really a useful theorem for intentional properties. Rice's theorem follows immediately from this, but the consequences for intentional properties are more fun. So for instance, one consequence of our result says that any decidable set containing all programs that run in polynomial time will contain infinitely many programs for computing any other computable function. Now, what does that mean to you? It means that if I pick one of you at random, and you write a program that you claim can decide an over approximation of the polynomial time functions, okay, so it decides whether you get, programs. So you get your program gets another program as input. It definitely says yes if that program runs in polynomial time. It might also say yes for some other programs, but you hope that everything will go fine. Okay? So one of you does that. Then another one of you writes any program at all. Any program at all. Now, the set of programs that guy number one's program will say yes on will contain some program computing the same input-output function as guy number two's program. Any computable function. And I can say this with dead certainty, even though I don't know any of the involved programs you made. Now, why does this destroy the pipe dream of having an over-approximation of polynomial time? Well, because it means that you are going to have in your set that over-approximates the set of polynomial time programs that compute any possible computable function, even the ones that are really inefficient. Like a program that takes time Ackermann's function of Ackermann's function of Ackermann's function, what do I know? So this is another consequence that essentially destroys people's hopes and dreams, as we like. A slightly more prosaic consequence, and I'm not going to tell you exactly why, but trust me on this, is that any decidable set of programs that contains all programs that never send any email must also contain a spam bot. So again, a naive dream you might have is that you can write a set of programs and you're certain that they will never interfere with your system and send any email. Unfortunately, every program or some program in your set will also be a spam bot, and there's no way around it. Okay, and I can say this again with dead certainty without even knowing what programs you write. Okay, so this was an example. Now, coming back to the abstract, and for those of you who are already dozing off, the first part, the first paragraph is the longest. Okay? So don't worry, you'll get beer soon. In the abstract, I also wrote that it contains the mathematics governing computing in this universe and in other universes you may dream of. So let's dream of something. Let's play a game. You are all gods. You are the alphas and omegas, the beginnings and the ends. And of course, like any god, you have a day job. So you go to your god office, and your deity in chief, your god boss, tells you the following. There are two rules. Rule one is, if you see an A, you may change it to f of A. The other rule is, if you see an F, you may change it to G. Those are the rules. You may change them, you don't have to. And then he starts giving more orders. He says, for this day, please start with an A. Then from the top, use rule 1 until you cannot use it anymore. Okay, you think, this is going to take a long time, right? Because you already realized that rule 1 says, oh, A, change it to F of A. Okay, but then that also contains an A, so I could rewrite that. Oh, damn. So you will basically take an eternity. But being gods, you are not constrained by the coils of mere mortals. So your boss says, when you are done with that, in an eternity, please use rule 2 from the top until you cannot use it anymore. So what does this mean? It essentially means that you have to use 2 eternities. So if you start with an A, you can change that to f of A, right? Then there's an A in there, you change that to f of A, but then you have f of A. That still contains an A, so you change that A to f of A, so you have f of A, and then you continue. Having spent an eternity doing this, you have obtained an infinitely long string, f of, and so on. Okay. You are a god, so this doesn't bother you. You continue, right? So rule 2 says that you could change an f to a g, and he asks you to start from the top. So you just start from the top and change the first f to a g. So we now have that f of, and so on, is changed to g of f, and so on. Then you take from the top is g, right? Then you take the next f, you change that to a g. So you get g of f, and so on. And after having spent 2 eternities, you have obtained a new infinitely long string g of g. Right, so this is a fun game at the job for gods. Now, it should come as no surprise to many of you at least that the length of such computations is something that's well defined using sort of fairly standard mathematics. The length of what we've constructed will be something called omega plus omega. Now your boss could have been nasty and given you other rules, and he could ask you to compute in a different way, and he could even have asked you to do this sort of an infinite number of times using other rules. So you could have spent an infinity of infinities, omega times omega, and you could even go further. However, being a clever little bastard, you say to yourself, well, I could just ignore how he told me to compute this, and just compute the whole thing from the start. How? By alternating rules 1 and 2. So you could start with A, transform that to f of A, that's rule 1, then use rule 2 to get g of A, then use rule 1 again on A to get g of f of A, then use rule 2 to transform the f into a g, so you get g of A, and you could just alternate that, and you would be done in one infinity. So of course you are gods, but for every pantheon of gods, there is a Prometheus. Right? Remember that Prometheus stole fire from Olympus and gave it to mankind. Now, a human can write programs that do the work for you. Sorry, and yes, these programs can even continue computing after an infinity has passed. We can write programs that do that in a very well-defined way, and we can do that if you're a logician for any so-called ordinal smaller than the Church-Kleene ordinal. We can do it. Okay. Now, what if I told you that a human could also do the dirty trick that you did? And even in a very strong way. A human can write a program, one program, that no matter what rules and instructions your deity-in-chief gives you for computing these things will automatically transform any computation into one that only takes one eternity. So your boss tells you to do something, and a way to do it that will last for an eternity of eternities. But the pesky human's program will then take those instructions and then make sure that they can be done in only one. Now, why don't we have a look at that? So, whoops. I have some code. Now, you will have to trust me a bit when I say that I have a program that basically does what your boss tells you. And the reason you have to trust me is I'm not showing you the code, I'm showing how it computes. And of course, since we only can stay here for part of one eternity, it'll only do the first part of the computation. Right, the ones that change the A into an infinite strings of Fs. But trust me when I say that if the computer had an infinite amount of time, it would actually then continue. So, and just to warn you, when this happens, because computers are really efficient, what you're going to see is just its computations very, very fast, so I'm going to break it after a while. Okay. So let's just make sure it's correct, okay? Oh, here we go. Now, if you look at the top here, you can see that it actually does what it's supposed to. A is changed to f of A, which is changed to f of A, which is, and so on. And it just continues. And it would have continued forever if I hadn't stopped it. Now, I also have a program that will basically analyze the instructions that your deity-in-chief gave you and tell me what the final term of the entire computation after 2 eternities is. And again, you will have to trust me a bit because I'm just showing you the computation. Remember that what we should get now is an infinite string of g's. And as you can see, it's a lot slower. And this is obviously because it has to analyze the computations that it gets and say, okay, what's going to happen in 2 infinities? This is going to take a while. I told you also that Prometheus had a program that would take any instructions that your boss gave you and compress it to only 1 eternity. And the example we had was this trick of using rules 1 and rule 2 alternately. Now I'm telling you that the program I'm about to show you actually does this analysis on its own and then does the clever reduction. So let's just do that. Now, system A underscore F underscore X is just an encoding of the rules your boss gave us. And C-red1 was just the original reduction, right, that I showed you before. So again, this takes a longer time because it has to analyze a couple of infinities ahead. But as you can see here on the cursor, it basically does the clever trick. A goes to f of A, which goes to g of A, which goes to g of f of A, which goes to g of g of A, and so on. And it does so automatically for any kind of instructions that your fellow god might give you. Of course, there are limits to this, and the limits are that the instructions that your god has to give you has to somehow correspond to something a computer can eventually do, even if a computer would use an infinity of infinities. Now, I have cheated you. I told you this would be a world you could dream of, but this is very much the world of mankind with actual computers. And there is actually also some kind of practical thought behind this. So standard constants like pi or e have infinitely many digits. And natural algorithms of computing them basically say, yeah, just compute as many as you like, and we'll just break the computation whenever we have got enough digits. And in general, when doing this, maybe not for pi or e, but for other infinite lists of objects, you might want to make several passes over the list. Right? You first do an infinite number of transformations, then afterwards you do an infinite other number, etc., and you stack these on top of each other. And obviously, you only want to do this in finite time. So this little clever program that Prometheus has made actually makes you do that. It lets you stack an infinite number of computations that run over the entire list and compresses them to one that only runs over the list once, which you can then break when you want. And of course, Prometheus, in this case, is a man, so this is my friend Jeroen Ketema, who actually wrote the code that I just showed you in a paper that we will publish, hopefully very soon. Now, we're getting there, don't worry. I also promised to tell you why the theory of computation is often irrelevant, and why that's a good thing. Well, remember mathematics. Computer science started from mathematics. It was born by mathematicians from mathematics itself. And there's an old adage that that mathematics is the queen and the handmaiden of science. It's queen because it is pure and abstract. Handmaiden because it is used by many other sciences for ancillary things, for helping them do their own science. And computer science is, in that sense, like a little sister to mathematics. It is like a princess and slightly smaller handmaiden. However, the influence also flows the other way. I have talked about dream worlds, but these were grounded in this actual universe, right? I showed you code that actually ran. Now, mathematics has no such concerns, right? Because mathematics might talk about possible worlds, and advances in the theory of computation has actually influenced areas of pure mathematics that have adopted notions of computability inspired by, but distinct from the ones we use. Notions of computability that have, well, not much to do with the same kind of computation that we do, right? There might be intersections, but they're different, right? This is not the same as some of the spurious ideas you sometimes see where people claim to have models that in actual reality compute more than, say, Turing machines or computers. These are often made by charlatans using the word hypercomputation. It's not the same. Again, mathematics will never claim, or pure mathematicians or logicians who work in these fields will usually never claim anything about the quote-unquote real worlds, because this is not their concern. Now, I said earlier that we, with the Danish term, had sejret os selv til døden, right? Everyone in the Western world is carrying one of these. An advanced laboratory for doing science, our science. But there's also another victory here, which is just as great, which is that we were born as a science from mathematics. And I can think of few greater accolades than sort of being able to influence mathematics back, to actually do something to our parents. With that, close your eyes and just breathe out for 10 seconds. I mean it. I'll take time. Relax. Thank you. this talk is videotaped. And I was going to say at this point that the reason you should relax was because we had just reached a climax together. Obviously, I can't say that on video. Well, so the climax of being proud of the fact that we have influenced our parent science as well. I promised you to speak about the greater good, right? The final part, just a few minutes, will concern the particular professorship inaugurated, this job, and how I intend to use it for the greater good. Now, the theory of computation in general is indifferent to humanity, right? The theory of computation would be no different if humans had ever existed. They might have used different symbols, the other intelligent beings creating it. They might have arrived at the same concepts in different ways, but it would more or less be the same. It will also be the same when our successors use computers or are computers themselves, as might happen in a few years. So as professor of theory of computation, I truly could not care less about you. Really, humans don't matter. However, computer science is much more than theory. And even some theory very much concerns itself with humans. And I, as a human being, care very much about you. So, as Mads mentioned, parts of the things I do which are completely unrelated to the theory of computation are also very important to me. I work in human-computer interaction as part of the section on human-centered computing. We generally concern ourselves with humans who engage with technology. We build new interfaces, we test them, we do experiments that help us understand how humans interact with technology and computers, and we change the interfaces. I also work in information retrieval, which is roughly the study of how humans can organize information and create algorithms that enable them to service their information needs. What we truly focus on here at DIKU, as you can see, at least part of the group up there led by Christina Lioma, with me just below on the image group website for some reason, is to look at rankings, right? So when you use Google and you put in some search terms, you will get a list of ranked results stating, okay, these websites or documents are the most relevant to your query. What we do is basically the back-end mathematics that helps these rankings become better suited for your information need, so that when you look at pornography, we will truly find the best pornography for you among the top results. You might strike that from the actual videoing. Okay? So these things very much concern themselves with humans. Now, let me recount to you a story. So the story is an amalgam of many different conversations I've heard at the primary conference of human-computer interaction called CHI. It goes like this. You have two scientists in the same field, human-computer interaction, but in different subfields, or even different subfields, talking together. One of them says, your field lacks external validity, reproducibility, and any kind of methodological rigor. And of course you know that what they're really saying is something else, but you can't say that in public. Namely that you're a bunch of pot-smoking hippies whose work has no bearing on anything except the actual people you observe by smoking the aforementioned pot. Then the other person, also working in human-computer interaction, but in a completely different subfield, says, well, your field is completely decontextualized and therefore ultimately practically irrelevant. Decontextualized means that it studies things in a way that is removed from the actual context of use. And of course what they're saying is really, you did a lab experiment on 12 white male middle-class college students and did some dubious number cooking on how fast they could solve contrived exercises in MS Word. And this obviously has no bearing on reality. Now, this comes from human-computer interaction, but this is just one example. It happens everywhere. It also happens in pure mathematics. So Giancarlo Rota, who is a renowned professor of mathematics from MIT, at one point in his life worked on something called order theory. And order theory has a subfield called lattice theory. And at one point in the hallways of MIT, the best technical university in the world, he was stopped by a very senior colleague who said to him, admit all lattice theory is trivial. Right? A personal attack saying that what you're doing right now is stupid, don't do it. So it happens everywhere. This is something that you in general want to avoid. Now, I have learned a few lessons. Mads early on told that I had served as deputy head of department for a number of years, so I've interacted a lot with very senior people from other sciences at very high positions in management, and I have interacted with sort of ordinary scientists in many different scientific fields. And what you learn is that when people navigate in a hyper-competitive environment, such as a university, in a highly politicized context, where office politics are taken to the next level by, say, the dependence on external grants, on personal goodwill, and so on, certain things or phenomena tend to happen. Well, one observation is that scientists are overwhelmingly willing to force their own criteria of success upon fields they know nothing about. Biologists are asking mathematicians why a, say, world-class mathematician from MIT who only has an H-index of 13 should be hired at the University of Copenhagen, because the biologist uses their own criteria of success, and the other way around, mathematicians might ask biologists why they don't start learning statistics before they actually use it in the papers. A second observation is that the capacity of people to pass judgment in research fields they know nothing about is seemingly unbounded, even when sub-fields of the same scientific field. And this is really annoying, right? Because you go from a wide-eyed student who just wants to learn, and then 30 years later, you are a narcissist, psychopath, bigot who only uses your own criteria of success in order to evaluate other people. A third observation is that true cross-disciplinary research only happens when all parties understand at least the basics of each other's fields. So all of these projects that involve people from different faculties who know nothing of the other guy's sciences are useful for few things. One thing they're useful for is getting money, but not doing a lot of science. So some advice to students would be, well, it's a wonderful webcomic here called Saturday Morning Breakfast Cereal. Basically says that, yeah, well, the solution is to listen to people about the area of expertise and otherwise be wary, right? Asking a chess grandmaster about the view of America's war strategy, and he would say, yeah, just use the bishops, right? They can move diagonally. That doesn't help you. And some very good advice to professors is that you should be careful what you judge. Your undergraduates likely have a broader knowledge of contemporary computer science than you do, so you tend to look very silly. Of course, these undergraduates will be brainwashed once they got the PhD, but that's not the point. So a true working environment where cross-disciplinarity is in focus, that actually gets some good science done, needs to be performed by people who not only respect what the other guys do, but actually know what they do and learn it beforehand. So in this job, apart from doing my scientific work, I will also try to do the greater good. So what will I do? Well, fields of research can occasionally be insular with great success. They can be isolated, but people in academic departments in general cannot. It doesn't work. I'm a theorist third. I'm a computer scientist second, and I'm a scientist first, meaning that I should remember what science is about and less about my hyper-specialization when I actually go and interact with people. And I will try to understand what you do and why it's important and why it's done in the way you do it without passing judgment or without foisting my criteria of success. And conversely, I will relentlessly browbeat you as a colleague to do the same to yours. Okay? All of the above are just about intellectual curiosity, the ones you as professors had as undergraduates and maybe lost along the way. I think that our department has come a long way since I was a student. When I was a student, well, our department and others had a degree of tribalism. And various generations of management have done a fantastic job changing that. But you still see, not here maybe, but a lot abroad, that the same things are still in effect. And for a truly visionary department to progress and do world-class science, this is something that needs to be, well, we all need to work towards the greater good. And with that, I would like to thank a few people. Science is not something that's done alone, so thank you to my collaborators from DIKU, from the Information Retrieval Lab, from the Image Group, Brian, Kasper, Christina, Niels, Evgeny, and Ingemar when he's here. The entire age to mention, except Sebastian, who's not here, but who would kill me if I didn't mention him, and to my family. But first and foremost, because this is an inaugural lecture on the theory of computation, I would like to thank my local group. So Christopher, Cynthia, James, Shanive, Jonas, Noy, Tobias, Thomas, and Thomas. Thank you, those of you who are here and are not traveling to conferences. I wish I had more time for you, and I'm sorry for only talking about the easy stuff today. And thank you all for coming. Beer will be served in the auditorium later, but Mads has warned me that there will be time for a few questions. Thank you.
So now you are warned by Jakob that you are in between him and beers. But we do have a couple of minutes.
We're not allowed to serve them until 15 minutes from now due to the
So
rules.
please go ahead.
So you mentioned page ranking, that we want to find what is most relevant. But one of the consequences of this undecidability would probably or apparently be that there will always be something completely irrelevant that will be seen as primarily relevant by whatever algorithm you can make for that.
In short, yes. In long, yes, comma, but. So these impossibility results tend to be of high theoretical interest, but sometimes of limited practical interest, because you can always, in cases like this, create fairly good approximations where you can sort of drown the irrelevant results in a sea of relevant results, or on Google, well, drown 1 in 9 relevant ones.
Go ahead.
You mentioned this over-approximation idea that if you cannot find the exact categorization of, say, whatever is in P, then we might, in theory, be able to make a slight over-approximation and saying, no, we cannot. And I assume the same is true for under-approximations by simple logical
Yes,
notation.
exactly. So you might have, and you could sort of even push that idea further. You can say that if you take some sort of more specific class, like the, say, class of quadratic time programs, you are going to get constant time computable functions in there as well.
You've been very theoretical. You've been very
It goes with the territory.
Human-centered. In other words, I would say, well, one way you combine computers with human is the human-computer interaction.
Yes.
Theory. Another way would be to go the Douglas Hofstadter way of artificial intelligence and Gödel, etc. Are you working in those directions at all?
So, in short, no. In long, in slightly more long, yes, but the ideas of people like Douglas Hofstadter are usually applicable only to a certain degree of relevance, especially for actual experiments with humans, where sort of the modeling aspect, where you use things like, well, Gödel's incompleteness theorem, tends to again be drowned out in a sea of practical results, which is also why you should be very careful of trying to, say, use theories from one area of computer science in completely different areas. Incidentally, Douglas Hofstadter is a fantastic person, but I worked together with his first PhD student a while back, Don Bird, who's a musician, among other things. And as part of that, Don showed me a picture of him being supervised by Douglas Hofstadter way back when, and he showed me a string of pictures, all of which they were high. They literally had, were smoking at the time. So I think that when Hofstadter did his most important work which was then about 10 to 15 years later reported in Gödel, Escher, Bach, and those books. Many of these ideas were conceived in a time of free love and free hash, but very little experimentation with actual humans. And this is not a criticism of Hofstadter, it's just the way the world was in the 70s and 80s and late 60s. Mm-hmm.
Okay, thank you, Jakob.
Thank you.